Okay, so thank you all for joining again. So we now switch gears a bit, and I'll let Alfredo take the lead. So Alfredo is an assistant teaching professor of computer science at NYU, Quran Institute of Mathematical Sciences. Alfredo is devoted to free education and teaching via Twitter and YouTube. He has created several resources and just recently pushed his 2021 spring course of deep learning online. Which is amazing, and I watch you all. I encourage you all to watch it. And then finally, he's writing a textbook with Michael Henaf, if I'm saying his last name correctly, who's a research scientist at Facebook AI, and Yan LeCun, who's also a professor of computer science at Quran Institute of Mathematical Sciences, working with Alfredo on research topics as well.
All right, so, thank you, Christina, so much for having me here today. So hello everyone, we have 66 people in class, and as you figure, this is an interactive session, and in order to be interactive, you will have to interact with me. Although we are digital, I don't care, we will be able to communicate as I do with my own students for in class, okay? So, I will look in the eyes, each of you, right there, and then you will type your answers in the chat such that I can read them. And then I can interact, because if you start talking all together, then it's going to be a mess, right? But I can read you because it's going to be sequential, right, in the chat. So you will have to guide me and guide this lesson and the next lesson, like on Friday, such that I can better address your interest and your preparation, right? So, for example, today I will give you this kind of introductory lesson about machine and deep learning, assuming very little knowledge about the topic, but I will assume that you know linear algebra, you know calculus, you know how to take derivatives, because you're a physicist, right? So you must be very skillful on with these things, right? But anytime something doesn't make sense, my accent is weird, you don't understand a word I say, right? Type in the chat, ask me to clarify. If you don't communicate with me, then it's going to be a monologue. Well, it's going to be still a monologue anyway, but at least if you provide some text, there's going to be a feedback loop, right? A negative feedback loop, hopefully, such that we can better focus on what you want me to speak about, right? If it's understood, you have to press the thumb up. So on the bar, on the Zoom bar, on the bottom right-hand side, there are reactions, right? You can, clap, you can give me thumbs up, thumbs down, you can tell me to go faster, slower, send me hearts, you can send many things, right? I can see all your reactions. Just 3 people are reacting right now, right? So I have no idea what the rest of the class is doing right now, right?
Alfredo, do you want me to enable the chat on Zoom, or is it okay for me to monitor the Discord?
Oh, no. Please turn on the chat, because I use the chat for teaching.
Okay. Yeah, we disabled that because we were expecting a huge amount of people, but I think that there is a reasonable amount for us to interact today via the Zoom chat. So
yeah, I need that. Otherwise, I don't know what's going on the other side.
Fine. Just give us a second. Yeah.
Okay. All right. So let's get this feature enabled such that we can start communicating. All right. Maybe I should have communicated with them logistics before.
Yeah.
I didn't know you can disable the chat. So, all right. So while we are waiting, I'm gonna be starting to share the screen. Desktop 1, and then we go here. Then we can close this and let me know when the chat is available, because I cannot see the chat.
Yeah, we're working on that. I think it's Paul Rivenberg that can enable the chat, who's the host of the meeting. I'm the co-host, so
okay.
I'll just give him 1 minute.
Sure. At least I can see your reactions, and we saw that those were working. Okay, so actually, while we are waiting, let me share with you where the material is. Right, everything is online, so it's accessible for everyone. Right, let me share with you this stuff. So first, so if we go on GitHub, and then we we type ATCOLD, @cold, okay? You should be finding my big face here. And then there is this PyTorch Deep Learning, which is the first repository with 5,300 stars. You should click on the stars such that those stars increase and many more people can see this interesting and useful material, okay? So here you have like a collection of different notebooks. Today we're going to be covering, I believe, the number 2, number 4, and maybe also number 5, okay? For the next lesson, which is going to be Friday, you can decide which of these topics you'd like me to cover. And to have a full syllabus of all the possible topics, you can click down and there is like a companion website over here. So these things open up. You can choose between several languages, has been translated. But anyway, if you scroll down, you have all this practicum. There are different topics, right? There are convolutional networks, there are recurrent networks, there are autoencoders, variational autoencoder, generative adversarial networks, control. There are many other things, right? This is from actually 2020, and then there is a 2021 version. So if we go, let's even go back to the GitHub, and if you go back to the first page, there is this NYU 2021, okay? And these are more recent notebooks. I have a different version of the variational autoencoder and the optimal control. And then there is a new website we can find at the end here. And here you have more topics, right? So yeah. So here there are more topics you can check and let me know which of these you might be interested to hear. If there is no major agreement, then I will pick something that is, you know, most popular between the requests, okay? So all of this is free material, it's online. All the material has videos as well on YouTube, such that you can follow along for, you know, any topic, okay? So is the chat available? Let's see.
So Paul is mentioning that he just tried enabling the chat, but we are not seeing anything happening. So
okay, then I'm not sure how we can interact on this thing. All right.
Alf, I mean, Christina and myself can monitor the Discord.
Yeah, but then if I ask questions, I don't know.
Let's use the raise hand feature and I'll unmute participants for questions. Okay.
Yeah. All right. So this is gonna be, these are the notebooks for later usage. Okay. So I would paste this link in the chat, but we don't have. So let's start with the introduction of the topic, right? What are we talking about today? Let me move this bar away. All right. And this thing. All right. So foundations of deep learning. What is this stuff about? So again, if you don't understand anything, just interrupt me or, well, somehow interact with me. And you can just call me Alf, right? If my name is too weird, too long, right? Moreover, as Christina mentioned, I'm always very active on Twitter, and this is my Twitter account where you can find educational material coming up basically on a weekly basis, okay? So if you're interested in learning more and more, just follow up there, and you know you have more content, and as well on YouTube. Anyway, so we're gonna start with a big picture of the field in order to figure out what are the different paradigms and different techniques, and you know, a little bit of introductory material, right? Because again, I'm assuming there is not much knowledge between the audience among the audience about machine learning. So let's figure together what this machine learning is, right? And we start with the paradigms. So there are again, let's figure first what is this machine learning, right? So in classical programming, you're going to be writing a program on your computer where you will basically specify some rules that are, you know, computing, let's say, the force given the mass and acceleration or whatever you want, right? So you have some maybe physical equation or something, and then you will write down these rules in some language. And this is basically called the algorithm, right? That the machine is going to be performing. And then we're going to be they're providing a lot of data usually, right? And then with this data, we process this data in order to compute. So these are the input of our classical program, and then we are going to be computing those that are the answers, right, or the outputs. In machine learning, instead, we do something similar but different, right? What do we do? So we still have the data. Of course, we have data, right, on the input side. But then what we provide the machine, it's also the answers, okay? So the answers, which were the output before, we provide them as part of the input, right? So that's kind of funky, I would say, weird, right? And then, so what do we expect, right? So we had 3 elements before, we're gonna have 3 elements also now. And therefore, we have the rules, right? So basically, our outcome of machine learning is going to be learning the algorithm that is connecting my data, my input, and the expected answers, right? So I have some target answers, my expected answers that I'd like to provide. So I provide those plus the input data, and then the algorithm will learn which are the rules that are connecting these 2 inputs. And again, is everyone following so far? But I'm not sure I'm able to teach without the chat. All right, thumbs up, thumbs down. Let me know if everything is okay so far. Cool.
You have no questions in the
oh, okay.
okay,
thanks. All right, so there are different learning paradigms, right? What does it mean? Well, we figure that very soon. On the left-hand side, we have something called supervised learning. Then we're gonna have something that is called sometimes unsupervised learning. And sometimes it's also called self-supervised learning. And then at the right-hand side, so we have this thing called reinforcement learning. So how do we distinguish between these 3 categories, right? So the supervised learning, first of all, on the left-hand side, as input to this green box, we're gonna be providing some x's that are in bold and pink. So these are vectors. And these x's are my observation. It's what we provide and we observe during training and also during testing and during like whenever we use this machine, right? So we always observe these pink observations. And then we also provide what I showed you just before, something that we can call as targets. If my computer, okay, there you go. Something that are the targets. So the targets are in blue and are again these y's, this bold vector, bold blue y's, right? That are vectors associated to my observations. And so the machine will produce some approximated y's, right? So like more or less like with the tilde symbol, right? Okay, no, it doesn't work my keyboard. So we have this predicted target, no? This y with a tilde on top, right? And so again, the outcome will be basically try to predict what are the target associated to a given observation. So question for the audience, why do we produce the target, the predicted target if I provide the target, right? So who can guess this answer? Why do we provide? So the question for the students is like, why do we try to predict this y tilde if I provide my y tilde here? So something doesn't make sense, right? And again, I don't know how to read your answers right now.
One of the participants is typing a question into Discord now. So
okay.
Let's see what they asked.
To evaluate how well the algorithm was learned, or so that you can make predictions on unseen observations.
That's the right the answer I was actually looking after, right? So in this case, this is
Good
my
job, Andrew.
There was another to evaluate if the rules actually work.
That's also very good. So in this case, basically, I'm showing you the training configuration. In the training configuration, I will provide both X and Y as input. So it's an input pair. And then I will try to get this predicted output, right? And then, of course, in order to be able to make sure that the predicted output is correct, I can measure the distance between this predicted output and my target, right? Target output. Well, input target, right? And then this is what I predict to be the target. And so by having both of them, I can measure the distance and I can tell how well or how bad it is, right? So I have a way of establishing the quality of my system. But then later on, instead, when I'm going to be using this supervised block in actually, you know, in the use case, not during training. So the training is when we learn things, when we figure out what is the relationship between X and Y. Later on, when we're using this machine, we will just try to predict a specific Y, given that we observe a input, pink input, right? So during training, we will always observe the pink thing and the blue thing. During testing, we only observe the pink thing, okay? Sometimes we may not have the pink thing at all. And so during training, we will just have the target, we will try to learn, but then at the inference time, we will just have nothing, right? Because as I said just now, the pink thing is going to be what you observe both between during training and during testing. So during training, we try to associate to a given pink item a blue item, right? So we have pink and blue, and we try to get them to go together, right? So when I train this system, this supervised network, I will figure out what is the blue item that is associated to my pink item during training and also during testing. Instead, what I said afterwards is that sometimes there are some paradigms where we don't really have this pink input, right? So what is this stuff? So this is what it's called self-supervised learning or unsupervised learning. In self-supervised or unsupervised learning, and someone has a microphone making noise in the background. So with self-supervised learning, we only have our target as input during training, okay? And then of course, we will try to estimate, to predict what is this input target, right? So this Y tilde. Again, the same question as I said before, why do I have the Y on one side and the Y tilde on the other side, right? Well, the answer is exactly the same as we just figured before. First of all, to evaluate the quality of the system. So I'd like to see how far my predicted Y is from my input Y. And also later on, when I'm going to be using this system, I will not have, of course, the Y on the input, and I will just basically evaluate on the right-hand side how good this Y I observe it is. Right? So again, this is very, very abstract so far, and perhaps I lost several of you. And again,
we have a few questions from participants in the chat, if you want me to read.
Yes, let me see if I can open the chat, because I have the screen on the PowerPoint on the other screen, so I am not sure how to. Okay.
So the question
it's on Discord. Can you share the Discord link somehow?
Yeah, you will find it in your email inbox. I just sent an email.
Okay, thank you. Okay. And Discord. Accept invite.
Yep. You just showed up. So you can go to the agenda text channels and the MLDL channel.
Yes, I found it. Okay. Yep. Let me actually try to use one single screen for the PowerPoint, because I have, again, the presenter screen on the other one. Presentation, slideshow. Set up slideshow. Presenter full screen. Okay, let's try this way. Okay. Okay. I see now. Finally. Okay. Cool.
Awesome. Thank you.
Yeah. This works then. All right. Hi. Why is there? Is why really an input? Hold on. Let me. Okay. Yeah, so okay, that's a very good question, right? So most of the time you're gonna be seeing people using in unsupervised learning the X as input to the unsupervised part, right? And usually Y is gonna be considered the, and of course, it doesn't work. My God, sorry. No, it doesn't work. Slideshow. Let's try this one. Okay, seems to be working now. All right, sometimes people will have on the self-supervised learning part, there is no cursor now, okay. In this case, people will have an X here and then a predicted X, right? This notation, that notation, although it's very commonly widespread, unfortunately is not correct. And I'll explain to you in a second why. So the X is whatever you observe all the time. You observe during training, you observe during testing. Instead, Y is only observed during training, okay? And so during testing, you will not have the Y, neither here nor on the other side. So what are we using this stuff for, right? So an example of this self-supervised learning would be learning a language model. What is a language model? I provide a lot of text to my model, and I will train my model to learn what is the next word in a sentence, okay? I will do next word prediction. In this case, no one provided me a specific input or annotation for my data. So we cannot really speak about supervised learning. We just use the whole data we have, which is like a string of information. And then we'll try to predict the future, the evolution of the information, right? The evolution of the English text, if I provide English, just by looking at the whole amount of data I have. Why is that necessary, or what is that useful for, right? How can we leverage a text model? For example, if you use your phone and you try to text someone, your phone will try to automatically predict what is the next word that you're trying to type, right? In that way, so that is basically a language model that is running on your phone, right? It's a next word prediction, is helping you typing things. But a more interesting application would be if we have like a speech to text recognition, right? So speech to text, we're gonna have possibly some dialogue in like some speech, sorry, in the X, the X data. We may have the Y, which is going to be transcription of the data. So we have a human being that has been writing down what is being said in the conversation. And then you try to predict that. If you do like simply try to predict the text from the speech, won't work, right? Because all the nuances of the grammar and the syntax, all the things are getting, lost. If you just try to connect the phonemes, right, the sounds I emit with the actual text, right? So there will be many possible connections, but only few of them will make sense, right? That's why if I would be now starting to speak Italian, you might not exactly understand, well, for sure you don't understand what I'm speaking if you don't understand Italian, but you wouldn't also be able to transcribe what I say, because there are many possible transcriptions, perhaps, that can arise from a similar utterance, right? From a similar noise I make, I mean, a similar sound, right? And so in that case, would be very convenient. It's going to be actually, you must use a language model just after your supervised learning, right? So your supervised learning module will try to predict the target, which is going to be the transcription given the speech. But then this transcription has to be validated somehow, right? By this unsupervised model, which has been only trained on text data, right? And so the self-supervised model has an understanding of what is the structure of the language, of the English language, right? And then if you plug this on top of this pink to blue, right, from speech to text, and plus the language model, then you're going to have possibly a okay transcription of what is your sound. Okay. So far everything should be okay. Is it okay? How is machine learning model different from a Markov chain? I never said it was different. Right? So Markov chain is one type of machine learning algorithm, right? We haven't yet talked about the different machine learning algorithms. That's next slide, okay? So unless there are more questions so far, I will try to give more context and give you a few more examples of these things, right? So we just mentioned right now that this self-supervised learning will try to find structure in the data, right? So in this case, we have a bunch of blue points, my target on this side, on the other, right? I don't know what these are, right? So they are simply points, but I can see they are somehow clustered together, right? And so I can train a system to figure what is the structure of this data, right? So it looks like there is a half semicircle on top and some sort of semicircle on the bottom, right? So my model can learn the fact that the data is structured in this way, although it doesn't understand what it means, but it can learn what is the expected structure, right? This is also very helpful if you want to do something that is called anomaly detection, right? If you'd like to find an anomaly in an experiment, right? Let's say you're measuring some collisions of things. Now we are fusions, right? Fusion physicists here. So you're trying to model some fusion of something, and you wonder whether the results you got are reliable or expectable, right? And so, or you have already an intuition about what is the expected range, what is the expected dynamics, what is the expected whatever, or you can completely disregard whatever is your previous knowledge. Let's say myself, I have no knowledge what you're doing, but I can train a model on the data of previous scientists or previous experiments or whatever, such that my model will learn what is the statistical correlation between the data, right? So I can learn the structure of the data, right? Such that if I have a new experiment, I can see whether it is fitting my model or it's like some weird quirk I'm getting, right? And so by training a model in a self-supervised fashion, right? Or unsupervised, if you use an older term, you can figure what is the structure of the data. And then if you get a new data point, you can basically evaluate how compatible or how likely that point comes from your, from your original data distribution, okay? And so this is kind of very convenient and very useful. And as well, it can be used in combination with, for example, supervised learning, right? So what was supervised learning, right? I didn't even tell you. So an example of supervised learning is going to be a classification. When we perform classification, for example, in this case, I will try to tell apart my red sample from my green sample. And for example, I can just put down a line. Okay. But then if I combine the two, if I combine the self-supervised learning and the supervised learning, I can do something that is rather cool, and that is basically how we are pushing now the forefront of performance of our models, which is with something that is called semi-supervised learning. Okay, so I know there are many names, but you will have all the slides at the end of the talk. In semi-supervised learning, you use the model you use here in the bottom part when you perform self-supervised learning, and then you use a little bit of data, which is this red point and the green point, which are exactly the same, as you can tell, right? These two images are the exactly same images with respect to the green, the red, and the blue point, right? But as you can tell, whereas my system before, when we were performing supervised learning, was just making a separation that was vertical, and this is called a decision boundary. Basically, it was telling that, oh, it's likely that the left-hand side should be red and the right-hand side should be green. And this is actually okay, I guess, estimation if you have this amount of data. What do I mean by this amount of data? Well, since when you perform supervised learning, the target are produced by a human annotator, right? And human annotators are expensive, right? They cost money, and I mean the data that they produce, it's crafted, right? It's created by some person, right? And therefore it has labor behind, and therefore it's going to be expensive, right? And so usually you end up in situations that are very, you have a very few amount of training data for these models. Human annotators, right? Yeah, so grad students, usually those are grad students, but again, it's becoming impossible right now to have enough data for training these systems, right? Because we are trying to train larger and larger systems, because the larger they are, the better they they tend to perform. But the larger they are, and they require more and more data. And data is extremely supervised data, right? Labeled data is extremely expensive, right? So all the self-supervised autonomous driving companies, the number one issue they have is with the sourcing of the supervised data, because it's absolutely daunting finding data for every possible situation that might happen on the road. It's impossible, right? So how can these companies make this further step and being able to deliver a fully autonomous car? Well, only by leveraging self-supervised learning, which is what I'm showing you right now. Okay. So as long as there is data, these blue points, regardless of their color, we said here, we can learn what is the structure, which is this kind of two U's, one on top of each other. Once we learn the structure, then we just need to have a few representative of these points, for example, this green one and the red one, and then we can extrapolate and figure out that all these upper points should be green, and then all these lower points should be red, okay? So by combining self-supervised learning and supervised learning in something that is called semi-supervised learning, then you can actually reach very good performance that are robust to noise, and they are stable, okay? Okay, so that was pretty much the big picture of the field, how it is these days, okay? A quick note about this reinforcement learning, which is something I don't deal with. There are two options. There are either the non-differentiable case, basically is trial and error. It's basically you want to think about this as playing a Super Mario on the Game Boy or whatever console you play, right? Maybe I'm too old. But anyway, so you try, you have game over, you try again, or game over, you try, then you start getting some experience from many game overs, and then you start maybe advancing through new levels, right? But the main point in this reinforcement learning is that you are going to be ending up in game over situations. If you want to train a system to drive a car, you can't really afford to crash a car, right? So reinforcement learning doesn't really quite work in the real case, for real case applications, like in the real life application, right? Games, yes, but not really real life, unless you have a differentiable solution. And then basically this is called control or supervised recurrent neural networks, or whatever you want to call it, right? And then that's what basically we use whenever we want to train a system to drive. Okay, so this was the introduction about the taxonomy of the different paradigms, right? Then we also can talk about these two, but there are the two types of supervised learning. We have regression. Whenever we have, let's say, a x-axis on the bottom, and then we have a y-axis on the left-hand side, and then I have some observations. These are the data I provide to the system. If I talk about regression, it means there is like I try to predict a scalar value given a input data. Okay, for example, this could be like the weather for let me think. Well, one example. Oh yeah, the price of a house, okay, given the surface area, right? So on the x-axis, on the horizontal axis, you have the surface area of your apartment, and then the y-axis are the different prices for different apartments. And I tried to learn what is the relationship between the surface area and the price of the apartment, right? In this case, it's a linear trend, right? Linear, what's called relationship. On the other side, so in this case, we said that y, it's a real number, right? So it's linear. In the other case, if we perform classification, perhaps I'd like to predict how many rooms a given apartment has, right? And so it's gonna be, you know, given a surface area, it's gonna have like tot number of like, I don't know, 4 rooms. Then it's more space, and it's gonna be like possibly a larger number or so of room, right? But the point is that the classification, when we talk about the classification, we usually talk about y as belonging to n, and that means y is discrete. It's not even sorted, right? So we can think about this as having different buckets we can associate our data with, okay? And we have the last slide on this deck here, which is a few algorithms, right? So there are things called artificial neural networks. There are things called super vector machines. There is decision trees. There are naive bias. I don't know how to pronounce the word. There are hidden Markov model. There are many things, but what I'm going to be talking to you today is going to be about artificial neural networks. So there are shallow and deep networks, right? So first question, then I answer the question I have here. First question for the students, why would anyone use shallow neural networks, okay? So on Discord, I'm monitoring the chat. Tell me why you may think we may be wanting to use shallow learning. What is shallow learning used for? Is it useful? Is useless? Is used? Is not used? Why did I include in this diagram, okay? Faster to train and fewer computations. Okay, that's actually a very good point. It is interpretable. Less compute, yeah. So for sure, whenever we're gonna be using like the networks on a phone or some devices, you want to have something that is fast, right? And deep neural networks usually have millions and billions now of parameters, and this means there are several gigabytes of neural network, right? This is ridiculously heavy thing, right? So it doesn't even fit on your phone. And moreover, we talk about shallow networks because that's how we started, right? Like 30 and more years ago, we couldn't compute so many. We couldn't. Yeah, we didn't have. What didn't we have that many years ago, right? So why can I talk about deep learning today, right? What are the key factors that allow me to talk about deep learning? If you have heard about deep learning, right? So as you figure, there are a lot of computations. In order to be able to do a lot of computations, you need a lot of compute, right? You need a lot of power, right? And so number one point that we are here basically, we are here mostly because there is NVIDIA, there are GPUs. What are GPUs? There are graphic cards. What are the graphic cards? The things you use for playing video games. But basically there are collections of many thousands, millions of little cores that are very stupid. They can do very few operations. They can do addition, multiplications, some comparison, not much else. But the nice part is that all these neural networks that I'm going to be introducing to you very soon are just a bunch of addition, multiplication, and comparison, okay? So here we are here today just because there are GPUs, there is the hardware. Moreover, there is data, right? There is the internet, there is digitalization, I cannot speak anymore, of everything, right? We have photos, we have videos, we have so much media online, right? So we have availability of data, right? Back in the days, you didn't even have cameras, right? Digital cameras. They were creating data set by drawing with the mouse on the screen, pixels, right? That was crazy. Third point, which is not to be forgotten, is the fact that we have frameworks, right? There is like something called PyTorch. There are another framework called TensorFlow that now we have JAX. So there are engineering efforts. There are not, neglectable engineering effort that are behind all this revolution, right? So right now, as I will show you very soon, I can pull up PyTorch and I can train a network in like 4 lines of code, right? Before, it was not like that, right? Before you had to write a few hundred lines of code, and not everyone is able to write those few hundred lines of code correctly, right? And so if you make mistakes in the code, well, you don't know if it's gonna be wrong, because it's not, if you have a mathematical bug, how did debug a mathematical bug? So you think your algorithm is broken. No, instead you just make a mistake, you put a minus instead of a plus, right? So, or you compute the gradient in a wrong manner. So the fact that we have frameworks right now that are doing all this kind of implementation of all the functions that you need, it's really a major point that allow us to be using these tools today. Finally, but it's not the less important, actually, I think maybe it's most important, the fact that there are so many investments, so much money invested in this field, that you have so many more people coming in, and so more people, more brain, more diversity, better the field, and more we advance. Okay. And so this was the introduction to the field, right? So how are we with time? So we have 1 hour more or less left. So I'm gonna be checking a little bit of these questions. Okay, that's a very good question, right? Avoiding overfitting. So what is overfitting? Overfitting, it's something that is basically you just try to memorize the data, right? So whenever you try to memorize the data, it's a problem, right? Because if you memorize something, it doesn't mean you understand something. You just know those 2 things were connected sometime in the past, but then you cannot tell if 2 new things you're observing tomorrow are also supposed to be connected or not, right? But then we figured that overfitting is not quite okay. It is a problem when the data is little, right? And then that's why the supervised data is little. That's why we're using this unsupervised data in order to pre-train our system to figure what is the structure of the data. And then we can just, give the little bit of information afterwards with the supervised learning, right? So what I showed you before here, in this case here, and of course, okay, forgive my clicking around. In this case, on the right-hand side, we definitely have overfitting, because I totally can tell these 2 are separated, right? It's very easy. But then the actual, correct solution would have been this horizontal one. And we can get the horizontal solution if we can leverage a lot of data, right? So it turns out that the more data we have and the larger the model, the better the system works, okay? All right, so let me see the questions. Are larger training data set required for deep learning? Yeah, so deep learning has huge models, and huge models are data hungry. And only with huge amount of data, you will be able to train very good systems, okay? And it looks like so far that the larger the system, the more the data and the better the performance, right? We haven't seen yet a slowing down, right? So it seems that scaling things up are is kind of always working very well. Okay. All right. So far, how was this lesson? Is it too slow? Is it too fast? You already know everything. You didn't know anything. You need to let me know in the chat here. There are only few people talking, because otherwise I really don't know what's going on your side, right? I cannot see you, right? So I cannot read your mind right now. So you should be giving me a little bit of feedback every now and then about what you think the things I'm saying are confusing, clear, weird, crazy, slow, fast, and so on, right? Okay, I think you like it. Fine, very good. All right, so let's give you a little bit of more concrete things, right? So a little bit of meat, such that we can eat a little bit, right? And let me see. Save. Okay, wow, I just closed the presentation. Didn't know that, and let me try to start the other presentation. while keeping the slide thing open. Window, okay. All right. Okay. Everyone know how to access Discord, right? So if you don't know how to access Discord, you should check the email from Christina and the thing, right?
Oh, yeah, or please do use the raise hand feature, and we can go ahead and unmute you, and you can ask questions interactively to Alfredo. Is that fine? Yeah.
Yep. All right. So today, in this second part of the class, right, I'm gonna give you some operating knowledge about how to get started with this everything, right? And again, on Friday, you can tell me what you want me to talk about, right? So we'll give you a few options, perhaps. You can choose if you are interested more in one topic or in another, such that you can, you know, get the education you want from me, right? I mean, I can teach you anything you want, but I don't know exactly what you want. Everything, again, I know it's on YouTube, right? So you can find me, just type my name and NYU. You can find all my lectures online. I usually have similar pace because I teach PhDs and masters, so it's like mathematically not advanced, but you know, it's not for it's similar paces today. Well, okay, we haven't covered any mathematics, right? So you see right now what's the pace. Anyway, so all the topics are there, but you have me live, right? So you can decide what you want me to talk about next time. Anyway, so anytime doesn't make sense something, just tell Alf, I don't know what's going on, just stop me in the chat, like write something in the chat. Right, so we start today second part with these artificial neural networks, supervised learning. We're gonna be talking about, starting with at least classification, right? So what is that I'm trying to do? So let's say I have this spiral, right? So these spirals are made of points, right? Where are these points living on right now, right? Answer in the chat, quick, fast. So I draw here some curves, right? Where do these curves live on, right? Are living in a 1 dimension, 2 dimensions, 3 dimensions? What am I doing here? Press enter. 3D. No, it's not in 3D, right? 2D, right? So every point here, every location is characterized by two components, X component on the X-axis and the Y component on the Y-axis. Moreover, I have a additional information. Can you figure what is the additional information over here? So there are the colors, that's correct, right? So every location doesn't, every point I represent on these curves, they have three information, three values, right? They have the X coordinate, the Y coordinate, and then the color coordinate. The color in this case is a discrete value that can only take three possible values, yellow, red, or purple, okay? So they are discrete values and they are not even sortable, right? You cannot tell yellow is lower than purple or whatever, right? So they are three independent values, right? In every point can either be yellow, purple, or red, right? Okay. And these are the equations to draw this line, right? So if we want to do that in Matplotlib, we know we should be able to do. Then we have capital K different classes, right? In this case, we have 3 classes. Let me make things a little bit more concrete and real, and let's add there some Gaussian noise, right? Just to make things a little bit more, you know, normal, right? Normal distribution. Okay, I'm joking. All right, so now you can actually see the points, right? So now there is some perturbation. You can see clearly the points I'm drawing there. So when I try to perform classification, given a X and Y coordinate, I will try to predict what is the color associated to that coordinate, right? So let's say I have a point here, over here. I will provide the X and Y coordinate to my system, and I will expect my system to tell me, oh, it's yellow, right? So first of all, I can simply do the simplest thing I can think of, and it's going to be using a linear classifier. What is a linear classifier? Well, simply I draw 3 lines like that, right? And these 3 lines, what could be used for, right? That's actually what we are going to be doing as well in the in the practical part, right? So why did I draw these 3 lines in this manner, right? What is the, what do you think the model will tell me for the bottom right corner? What is the model going to say? This color should be red, right? Okay. But unfortunately, you can see there are mistakes. Why there are mistakes over here? What are the where do the mistake arise from, right? Type fast. Press enter. There are things, you know, popping up, right? So the bigger problem here, okay, that's very good, Matthias. The data is not linearly separable, right? So given that the data is not linearly separable, you cannot separate it with the lines, right? And so usually what do people do? And then this is what I don't do, and then you see what I do very soon. Usually people say, oh, we have to use non-linear decision boundaries, right? So they start curving all these decision boundaries. I don't like it. What happened here? Yeah, you need Python, but I think it's gonna be easier if I will show you things running, right? And then in your time you can just try to run it yourself, right? So I would suggest you to just watch right now after during the lesson, and then afterwards you can try at your time, and then you can ask if you have any issue, right? It's gonna be much easier than doing all together, right? Because again, it's gonna be a bit crazy otherwise. Anyway, so people say, oh, so this is non-linearly separable data. We should use non-linear decision boundaries. I don't know how to do that because deep neural networks are just linear modules interspersed with some non-linearity. We don't know that yet, but we'll figure that very soon. So again, we mentioned that the major issue here is the fact that there are intersections, right? So again, I told you what we don't do. We don't use non-linear decision boundaries. What is the other alternative? What can we do otherwise? Tell me in the chat. So we want to avoid intersections. I cannot bend my straight lines. What can we do? Tell me. Okay, for in English. Okay, we can do segmented lines. That's actually one option. Let's say we want to, very good. I like Omstavan option. So one option would be using segmented lines, which is actually exactly what we are going to be ending up doing. Or the other way around, which is going to be what Omstavan says. We're going to be folding the space. We're going to be morphing the space. Okay, what am I talking about, right? What is this dude talking about? Let me show you a video of what I'm going to be showing you in a second in the notebooks, right? Let's see. Hop, and we move this one to the other window. You should be able to see something. I think so. Give me feedback. You see stuff, right? Yes, cool. So these are my data points, right? So before I show you 3 spiral, here I'm showing you 5 spiral. Why? Because it's more colors, right? I like it more. Right, let me play the play button, and I show you what I'm gonna be doing, right? So this is what I'm gonna be doing in this lesson today, okay? I'm gonna be taking this space, I'm gonna be morphing it, such that at the end of this morphing, you will end up in a situation where each of the spiral branches I show you will be collected in specific regions of the space. As you can see, this thing is convergent, right? And then when we are at this point over here, where every color has its own part, right? I can simply do what I was showing you in the previous slide, right? So this should be almost reaching the end, right? There we go. And then here I can show you this, right? I can segment this thing. And these 5 arrows are gonna be, you will tell me at the end of the lesson or next time what these 5 arrows are, okay? But this is what I'm gonna be doing right now in these lessons, right? I'm gonna be teaching you this. I hope you can, you like this and you're excited, and I don't hear you screaming or cheering, but I hope you are, okay, someone is cheering, but okay. So this is all there is about supervised learning, okay? We only have linear decision boundaries that are the straight lines. So these lines actually are the intersections of planes, right? So you can think about, let me give you this first, a little bit of intuition. The yellow thing over here on the left-hand side, it's a plane that is popping up, right? You can see me right in the chat, right? This is a plane that comes up that way, right? So you have a plane coming up that way. You have a green plane coming up this other way. And so there is intersection between these two yellow and green plane, and you have that line on this diagonal, right? Then guess what? There is another plane, the blue plane, coming up on the other side. And so of course the blue plane and the green plane will have a kink, right? Intersection. And since we have three planes which are not collinear, then we have a point as intersection of three planes. Then you have the red plane coming up on the other direction. So you have a line over here. And there is a line also between the yellow and the red. And then finally, there is a fifth plane coming up on the other side upwards there, right? And so you want to think about this as having 5 different planes. And when the plane is the highest in that region, then it's going to be the winning plane in that location, okay? So there are many planes popping up, and then that's what we are learning, right? Our system will learn to generate these planes, but then the data, which was all kind of entangled in the input, has to be untangled by the network. And so we learned that right now, how to untangle data, okay? Actually, let me quickly go through one of the notebooks, right? Such that I can show you a little bit more context. So this is the notebook. Where is it? The notebook I'm going to be showing you right now is going to be the notebook number 2, the space stretching, okay? So I'm going to be just executing through things, right? So I'm not really going to be explaining what each of these things are doing too much. Let me run this. I'm actually running a different version, so the results are a bit more colorful here. Okay. So if you check the instructions on this page, right, at the beginning, I will tell you you want to install Miniconda first, and then you're going to be activating and loading this environment, right, such that you're going to have all the packages and all the necessary Python modules that we are going to be using. And then I activate this PDL. What is PDL? PyTorch Deep Learning. Okay. So I just do that one. I do conda activate PDL, and then I open Jupyter Notebook. Jupyter Notebook is a nice environment to play with things, and it's going to be on the other side. Okay, and I want to show you random projection. No, wrong file. Random projections. Okay, so again, I'm going to be just executing things right now, and let me, oh, they're already executed. Okay, so in this case here, I'm just plotting you, I'm showing you a little bit of point, right? So let me hide the thing. Oh. So can you tell me where these points are coming from, right? I didn't show you the code. This is just mathematics, right? So you shouldn't be reading the code right now, okay? So these points are coming from you have few distributions we may use every day, right? So guess what distribution is this? Guess in the chat. You're still following, right? Gaussian, yes. It's a normal, actually, yeah, it's a standard normal, right? If it's a standard normal, and therefore here the actually average radius is roughly 3, actually 2 and 2 something, right? If you don't know why, then you should check why, right? But anyway, these are Gaussian normal standard normal distribution in 2D, okay? Then what I do here is simply a Svd decomposition to show you what happens if you multiply a Gaussian by a matrix, right? And I show you here the singular values of the transformation. So you have a stretching in one direction, well, stretching 0.7. So it's a compression in one direction by 70%, and the other one gets really tiny to a 10%. Here I show you another one. So the left singular vectors are gonna be something at like 45 degrees. Actually, if you see the color, right? So we have blue, green on the left, right? And here we have blue, green. Okay, this doesn't do reflection. Blue, green doesn't reflect. So basically, if you apply a linear transformation to some points, you basically squash them somehow, right? You rotate as well. Oh, blue, green, right? So in this case, blue is left, green is on the bottom. So in this case, the determinant of the transformation was negative, right? So we have a flipping of the points. Anyway, this stuff is boring, right? Oh, what happened here? It's almost singular, right? So this matrix is almost not invertible because it's squashing everything down to one dimension. Anyway, so we know how a linear transformation works, right? We do we? Yes, we do. Okay, good. So you can do exactly the same with PyTorch, right? In this case, I'm showing you how to use PyTorch, and I create a sequential module. A sequential module is simply like a sequence of operation where I put inside a linear operation that goes from 2 to 2, right? So it's a 2 by 2 matrix. Exactly the thing I was showing above, right? And so you get exactly the same stuff, right? This is just to show you that you can perform matrix, like a neural network in this case is just a matrix multiplication. Then we can add some nonlinearity, right? So what happens in this case? In this case, I'm using this function over here that is mapping things that are lower than minus 2.5 is gonna be mapped to -1, and things that are higher than 2.5 are gonna map to +1. So in this case, if I have this as my input, what is going to be the output, right? So this is 1, this is going to be 2, this is going to be 3 over here. We said that if the input is larger than 2.5, it gets mapped to 1, right? So tell me in the chat, what happens if I apply this, squashing function to these points over here? What do you expect to see? Type, fast. It brings the outer point towards the center. Yeah, but what is going to be the maximum value you can observe in every direction? It will not cut the data. Okay, that's correct. So you're going to be a box between -1 and +1, okay? And so this is what you're going to be observing. It doesn't cut, it basically squash everything into a box. In this case, my singular value of the, I have a basically identity matrix, so it doesn't do anything. And then I perform this squashing function. In this case, I use a scalar of 2, so I expand more the data, right? And then I push down, right? So everything now gets compressed in the corners, right? And more, right? So in this case, I managed to zoom in the center of my points, right? So all my points now in the center are very separated, whereas all the far away points are getting all squashed down into basically the edge of this square, okay? All right. So now the cool part. Guess what happens if you stack several layers of linear transformation and non-linear transformations, right? So you have like the linear transformation, like rotations, and then non-linear transformation, this kind of squashing. So rotation, squashing, rotation, squashing. Why am I talking about rotation? Because in high dimensional space, basically everything is a rotation. And so if this is my input cloud, I run the network and I'm gonna get some sort of funky things, okay? So, and in this case, I'm gonna use a deep network, right? In this case, I have 5 layers, 1, 2, 3, 4, 5. So actually there's gonna be 1, 2, 3, 4, 5, 6 layers in total because there is the input layer as well. And so in this case, you get your cloud of points, which gets curved, it gets turned, it gets folded. You have different shapes, okay? And so all of these kind of transformation are arbitrary right now, right? So no one told us how to make these transformations. They are arbitrary transformations which are, performed by our network. So in today's lesson, we're going to figure how to enforce a specific transformation, which is going to be computing, it's going to be performing the task we want, right? So before I show you that morphing of the space, right, the pretty animation, which was bringing my data in a linearly separable manner, right? In here, I show you that having a stack of matrices and nonlinear functions allows you to perform some sort of morphing of the space, right? And so the question would be, how do we select a specific transformation? So what are these transformation parameterized by, right? So what are the degrees of freedom of this transformation? Have you followed so far? So again, I didn't show you code, right? So what did we use right now so far? Two things, right? In this this notebook. Remind me here. What did we see over right now? There are two types of transformations we saw, right? If you scroll up, the nonlinear and the matrix transformation. That's correct, right? So we saw two different things. That's all there is to deep learning, okay? So there are linear transformations that are simply, converting a circle in a potato. And then there is nonlinear functions that are squashing things into boxes, more or less, right? And so the nonlinear function don't have parameters, right? In this case, I was just scaling the input, but the scaling of the input can be thought as the previous layer, right? And so we have linear layers, like we have matrices, which have parameters inside, values, right? And then we have this squashing function. And so learning, when we talk about learning or training a system, is going to be finding out what specific parameters we want to have in order to perform specific transformation of the data. Transformation that are going to be giving us linearly separable, for example, points, okay? So far, are you following? Are you with me? There are just 4 people interacting on the chat. I don't know about the rest. Tell me, type on the chat, how's it going? You follow, it's unclear. Should I move on? Should I repeat? Okay, going well. Okay, all right. So it seems like that it's going well. Okay, very good, very good. For Friday, we will have the chat on so that we'll manage to better. Okay, very good. We manage better interaction, right? So let's figure how to now make these enforce specific transformations, okay? Again, all the notebooks are online. You have to go over this in your time later on, right? The more I slow down in class to get you to run these things, the less we can cover and the more you will ask me later, right? So no, maybe you can ask anything you want, but I can give you more things. I can show you more things. Then you can choose what you want to play with, okay? If you don't want to play, then you can just don't play, right? Anyway, here. So we said we wanted to unwarp the thing, right? We'll get the chat on Friday's lecture. Thank you. So that's what we want to do, right? So this is the unwarping of the data, right? So how do we do this unwarping? So during training, what we will observe is going to be something like this, right? But I just said before, I want to use linearly separable, linear separations. What's going on here? So on the left-hand side, in this case, I change my point of view. So if you have a network, the input of the network is usually on the bottom side of the screen. Yeah, you can see me, right? So the input of the network is here. Then you climb the network. You have higher levels, right? You go high in the hierarchy, and this is the output. What I'm doing right now, I'm going to be basically looking from the top downwards, right? So I look how my data that is bubbling up the network gets warped by the network, okay? So that's what I'm showing on the left-hand side. I show you from bottom to top and back to bottom, okay? On the right-hand side instead, what I'm showing you, watching from the bottom of the network, I look at the linear decision boundaries and how they get warped as the network gets trained, okay? So left-hand side, again, I look at the data from either the bottom side in this case, or I go up, up, up. Well, the network basically gets the data unwarped on the right-hand side instead. I show you from the bottom side how my linear decision boundaries get warped when we train the model. Okay, I hope it's clear. Okay, moving on. Training data. So again, this is most important thing. That's the only thing we have. Okay, three things we have: data, linear transformation, which I call them rotation, and then non-linear transformation, which I call them squashing. Looks like on the left plot, all the points are in the correct area, but in the right side, some points were in the wrong place. Okay, so those animation, I made them, those are fake. Okay, these are just educational animation. The one I showed you before, the morphing of the space, that was real. Okay, those were just, you know, me making like those were in my mind back in the days, right? Then I actually made the actual full animations. The linear decision boundaries appear to be slightly curved. In which picture, right or left, Vincent? Right. Yeah. So they get curved during training if you watch from the bottom, right? Again, this is my network. I'm going to be explaining this in a sec, so just wait a second. All right, data, right? So we have to figure how to provide the data to our system in order to be able to learn the parameters. So this pink bold X is going to be always representing my observation, okay? In this case, we are doing, again, supervised learning. So we have X, pink bold X, parentheses I is going to be my ith sample, my ith observation that lives in this Rn dimensional space. I decide to put these things in rows in this big X, capital bold X matrix, okay? Such that I will have now n columns because each vector has n components, and therefore I will have m rows because I will have m examples, okay? So this is my design matrix. It's called in machine learning. We don't call it that way in deep learning, but whatever. On the right hand side, instead, I'm going to have my classes. Class can be 1, 2, 3, how many classes, how many items you have in your example. So in this case, I will have a vector C, bold orange C, and each example from 1 to m will also have a class associated to it, right? Can be pink, can be yellow, red, purple, whatever, right? So you have a discrete class associated to each input X. And so there are m of them, right? I'm going to be doing something that is called the one-hot encoding. What is this stuff? Well, simply saying that if you have 3 classes, I will give you, I will have this Y matrix where each of these Ys are going to be either 1, 0, 0, 0, 1, 0, or 0, 0, 1. This basically tells you what is the probability of being one class or the other. When we train these systems, and very, very, very often, we have this deterministic probability, right? So the probability mass, it's either 1 or 0, right? And it's going to be, of course, they have to sum to 1, right? So in this case, we train with deterministic data, right? We can do many other things, but today we're going to be doing the most trivial thing, right? And most straightforward thing to do, which is going to be having a specific single color per point, right? The point is red, yellow, or purple. This node doesn't have mixtures. So this is going to be the Y point I'm going to be using for training the system, right? So how many columns? Well, capital K, right? If I have capital K classes, I will have capital K columns. Right? I hope you're following. How many rows? And 1 per sample. And so these Yi's are going to be either 0 or 1, right? And then again, the sum has to be 1. So what is a fully connected layer, no? FC layer. So these are the most classical type of network, right? So we have my input at the bottom, X. I will have a matrix multiplication in a squashing function. So I have my hidden representation H. And then I'm going to have another rotation W, Y, and then I will have a final predicted Y, right? The tilde means is a more or less, the circa, no? More or less. And so these are the only equations you're going to be seeing today, right? So I have the hidden representation is the squashing function f of the affine transformation of the input x. And then the y tilde is going to be a g nonlinear function of the affine transformation of my hidden representation h. That's it. F and g can be any type of nonlinear function. We saw before a hyperbolic tangent. We can have a sigmoid, like a logistic sigmoid can be the positive part, which is called ReLU, rectifying linear unit as well. Or you can have something called soft argmax, which people call softmax, unfortunately, but it's soft argmax, no? People don't know how to call things. Anyway, I call it soft argmax, but everywhere else you will just say hearing the word softmax. Anyway, how does it work? You have the input, it's gonna be in pink there. Then you have the hidden representation. I may have second hidden, third hidden, then I have my output layer. And then the first is also called the activation at the first layer, second, third, fourth, whatever layer. And then to go from one layer to the other, you're gonna have this collection of parameters, weights, W, W1, W2, and so on, okay? And so how to compute the first, do F and G need to be monotonic? Yes. It's okay. The question is good. Yes, they need to be monotonic. Then, although I'm gonna be regretting this answer, because no textbook will say that. But anyway, yes, they should be monotonic. I'll let you know. I'll tell you later why it's important. It could be important. Anyway, how to compute the first value? Okay, this is simply again linear algebra. I'll try to go perhaps a little faster. So here is going to be basically multiplying this wj, which is the jth row of my w matrix, right, times the x, right? So this is going to be a scalar product, right? The row times the vector. So I have a scalar value plus the bj, the b coefficient is called bias, and which is, of course, we know what is scalar product, right? So from the x layer, not the input layer, we're going to have all these arrows, and each arrow basically it represents the strength that connects that given input to the first hidden value, right? And so these arrows are the weights inside the W matrix. And then how to compute the second one, right? Yep, thank you. So I appreciate Alf mentioning of y tilde as circa, meaning nets will never learn the exact y's, but only approximations. Yeah, that's correct. Yeah. Then we have the second value, which is going to be the, again, similar. We are going to have all these weights, right, connected to the second value, and then so on, right? And then here I spent, ages drawing this stuff in PowerPoint, and I regret it maybe. Anyway, moving on. We have all these values, and you can compute up to the end, right? I'm going to be going faster because we already know this stuff here. Yeah, getting there. So inference, how does it work, right? These are the two equations. H is going to be this, there should be y tilde, right? So this is wrong notation here. So H is going to be this squashing function of the affine transformation. Y tilde is going to be this G squashing function of this affine transformation. I'll fix the slide and I'll send you the link later. These are the matrices with the right dimensions. And then we said that we have these nonlinear functions, right? So you can think about this Y tilde, which is wrongly written Y hat in this case, is a function of the input, right? And so we can think about going from this Rn space, no, which was our plane. We had the X and Y coordinates, to this RK, which are the three classes. So we map my points, to the points to the color information. Usually what we do is going to be going from the input space to an intermediate representation, which is this hidden internal representation, RD, and then back to the RK, where RD is very large. This is so important, right? These networks need to be over-parameterized. You need a lot, large, long, deep networks. Why is that? Because otherwise the optimization process doesn't work. I'll show you a video about that as well in a sec. All right, maybe I'll show you now the video. Let me show you the video because we had 10 minutes left, I think. All right, So in this case, right, I'm showing you a network. Hold on, network stop. In this case, I'm showing you this network, right? Where I use the D dimension, that is the hidden dimension, equal to 2, right? So my data lives in 2D space. Then I have hidden representation that also live in 2D space. And then I project that to 3, no, for the hour classification case. You remember how nice, smooth the animation I showed you before it was? Now let me show you this one instead, what's happening. So in this case, this is my data. You can see how the space gets folded in very specific manner. Right? And trust me, those very angular folding places are absolutely a nightmare to optimize, right? So the optimization process, for me to give you this animation here, I spent way too much time. I don't want to tell you how much time I spent, because it doesn't work, right? This stuff doesn't really converge, doesn't get enough information to be able to perform the transformation that puts my data in a linearly separable configuration. And as you can tell, everything is really crammed together, right? You remember how smooth was that morph space before? And you can tell here that basically these are very singular matrices, right? As you can tell, right? So every time you get one dimension, okay, these are too much stuff. Every time you can see those dimensions disappearing, that means you have a singular matrix somewhere, right? Because you have the determinant that is 0, you kill one dimension, and that is a nightmare, because you will see, because we cannot go backward. We cannot invert, okay? We cannot invert that matrix, right? So since we cannot invert that matrix, how do you get information how do you get information to train the system? We'll figure that soon. But as I told you right now, we need to have this intermediate representation D to be most of the time much larger than my input and the output, okay? This is important, really important, because otherwise it doesn't work. All right. Let me finish this presentation and then I show you the notebook. So in our case, we said the input was living on a 2D space, no? R, N, N equal 2. Then we have a hidden representation, which goes in 100 space, dimensional space, and the final Y tilde, no hat tilde, has 3 options, right? How to train these networks, right? All right, so we use something called soft argmax, right? Which again, people will call softmax, it's wrong, which is simply the Boltzmann, right? Boltzmann Gibbs distribution. And therefore goes from 0 to 1, right? Exclude, right? So you take the exponential of the output of the network divided by the summation of the exponential of all the other, right? So the sum of all the exponentials of all items, right? So L, for example, is going to be the last output of my last linear layer, right? L for linear layer, or also for logit, which is, or logit. I like logit more. Anyway, so this is the output of the last layer, the linear layer, and then I compute the exponential of all of them, and then each output is going to be the exponential of that value divided by the sum of all the other exponentials. As you can tell, this converts an energy into a probability. You already know, you're physicists, right? I don't have to tell you this stuff. So how does it work? I'm going to have a loss function, which is telling me how bad my predictions, Y tilde, are, given that I know the original class, which is going to be an average of all these per samples losses, okay? What are these per sample losses? Well, those are simply, we can define it as being minus logarithm of the predicted Y tilde, no, in the correct class C, okay? So we have the correct class for the predicted probability, and I take the minus log, right? So you can tell now that if the probability here is going to be 1, you're going to have the minus log of almost 1 is going to be 0, right? Instead, if I get the wrong prediction, right, the log of something almost 0 is going to be minus infinity. Then you have the minus in front is going to be plus infinity, right? So what this item here tells you is that if you nail the correct prediction, you're going to have basically a 0 error. If you get the wrong prediction, this stuff is going to tell you plus infinity. You're doing a very big mistake, okay? And here I'm showing you, so this is also called cross entropy, negative log likelihood, can be called many things. So a quick example, but you know how logarithms work. So we have x is going to be my input. I'm supposed to tell you class is number 1. And then the my prediction is actually 1, 0. So the y is going to be 1, 0, 0, right? The one hot encoding. And my prediction, y tilde, is going to be almost 1, almost 0, almost 0. If I compute the loss of this stuff and I check the number 1, what do I compute? What is the logarithm of almost 1? What is almost 1? Well, 1 minus, right? So it's because it's not, you cannot always, you cannot reach the 1, right? So if you have a logarithm of almost 1, you're going to get 0 minus, right? Then there is a minus in front, it's going to be 0 plus, right? So this stuff gives you 0 plus if you get the correct prediction. Instead, if your prediction is going to be the wrong one, right? I predict there should be the second class. I'm going to be predicting what is 0, almost 0. Well, almost 0 is 0 plus. Logarithm of almost 0 plus, well, 0 plus is going to be minus infinity. There is a minus in front. This stuff is going to be giving you plus infinity, right? So if you make a mistake and you're very sure about the mistake, you're going to get a plus infinity loss. If you get the right answer, you're going to get a 0 plus, right? Almost 0. So given this information, how do we train the system? Well, with this slide. So I'm going to be calling capital theta the set of all the parameters, right? I put all the parameters inside this set. And such that I can rewrite this loss with a different name, right? This is going to be called objective function, but okay, same stuff. I just changed the variable, right? The loss tells me the distance between these two items. This one instead is going to be like a scalar value associated to a specific configuration of the parameters, right? Again, same function, well, same output, different names because it has different arguments, which is the one we saw before, huh? The cross entropy, the minus log of the output at the expected class, the correct class. So how does it work? So let's say we have this value for the j, you know, and on the x-axis, so this is my j of theta, and on the x-axis I have my theta. Let's say I start with this original value for theta. I call it theta 0. I will have a corresponding j of theta 0, right? I can compute what is the derivative. So this is going to be my derivative of j with respect to, you know, derivative of j with respect to theta computed at theta 0. And I can tell here the derivative is positive. And so with a positive derivative, I know I want to move to the left. And so I will use the negative value of the derivative, right? Multiply perhaps by a stepping size. And so this is called the gradient descent algorithm. This gradient descent allows you to descend down the slope, given that you compute the derivative at that point, and then you go in the opposite direction of the derivative, right? Okay. No magic. You should know. I think you should know this for error theory, right, in physics. How do we compute these derivatives? Well, these are partial derivatives, right? Because there are many items inside. So we simply use the chain rule in this case. And in the other case, we have to unwrap it a little bit more, right? And this unwrapping, so the chain rule in my field in deep learning is called backpropagation. Whereas the learning, the changing the parameters is called gradient descent, right? And so in the last minute, before saying goodbye, I show you how to run the notebook, right? So this is the repository we saw before, no? This one. I'm going to be showing you right now this spiral classification. So we have, it's already conda activated, so I just do Jupyter Notebook. And it's on the other screen. Okay. We say we open the spiral classification. We use the PyTorch deep learning kernel. I just execute everything. Kernel Cell run all. So what I'm showing you right now is going to be exactly what I show you in the example in class right now in the slides, right? So these are my points. First, I try to train a network which is having only linear layers, right? Here you can see there are only linear layers inside the network. Okay, so I have two linear layers going from N to H, and then N to D and D to K, right? So these are wrong letters. I should fix these letters. And so this is what you get, right? With a linear network. Of course, you get linear decision boundaries, right? Instead here, the only thing I've done is been adding in between these two layers a positive part, right? So this is just telling me if the number is positive, it gives me the number. If the number is negative, it gives me 0. So it's the positive part of a function. By adding one non-linearity between these two by adding a non-linearity between these two linear functions, I can actually get this. Okay, so this is crazy, right? By one line change, you convert your linear model, that is this one, that was not able to classify the points, into this stuff here, right? In this case, the network correctly tells that these points are yellow, these points are purple, these points are red, right? Very, very, very briefly, because I just want to show you that there is one more item in case you're curious. There is a regression notebook. Cell PyTorch deep learning, set kernel, cell run all. Okay. In this case, I'm training you regression system, which is very similar to what we just saw right now, where we're trying to learn this function over here, right? So this is like a definitely non-linear function. I like to learn what is the function that generated these points, right? And so in this case, I show you a linear model. So in this case, the model, as I showed you before, it's simply these two linear layers, right? So of course, it's going to be coming up with a line. So these are the two linear modules. And then scrolling down, I'm going to be adding now either a positive part in the center or a hyperbolic tangent, okay? So we have either the positive part or the hyperbolic tangent. And then if this system is still training 8, there are 2 more, I think. Let me see. 10, yes. 1 more, and then we are done. I took 5 minutes because we lost 5 minutes at the beginning. Sorry for stealing time. All right, there we go. So we have 2 models we're going to be comparing. There is the model which has linear, positive part linear, and then there is the other model which has linear, hyperbolic tangent linear, okay? And if I show you here, these are the untrained networks, right? So the untrained networks have arbitrary, transformation, like predictions. Then I train my system, and my system gives me exactly these 2 options, right? With the positive part on the left-hand side and the hyperbolic tangent on the right-hand side, right? So as you can tell, on the left-hand side, we have basically piecewise linear interpolation of these points, right? Because we use this positive part. Whereas on the right-hand side, our functions we are using as, what's called like the Fourier basis. Now, like the basis function we are using are these hyperbolic tangents. So this stuff looks more smooth. Something very important then for whoever is listening. What happens now if I go outside the training region, right? We train from -1 to +1. What happens now if I look at from -4 to +4? Disaster, right? Of course, it looks disaster. So in this case, you're going to be having in the positive part that these lines will go straight down and straight up. Whereas in the hyperbolic tangent, this thing will look like hyperbolic tangents at the end, right? So they will saturate at the end. In yellow, I show you what is the standard deviation between the predictions. And you can see the standard deviation increases after we leave the region, right? In both cases, right? So if you have multiple models that are trained on the same data, you can compute the agreement between these models to tell how far you are from the training regime. This is very powerful. Again, this is maybe too much advanced. So we reached the end of this introductory lesson on machine and deep learning. I hope you understood something because, again, difficulties interacting today, so I couldn't really follow much what was going on your side, but I think perhaps we managed to pull it off, right? You can feel free to ask questions on the thing here on the Discord chat, right? I will try to answer your questions. And for Friday, where we will cover possibly more advanced topics, we can talk either about transformers, attention, graph convolutional networks on grids, recurrent networks, whatever you want. Okay, so we'll send out a poll. We can talk about variational autoencoders. We can talk about self-supervised learning. We can talk about generative adversarial networks. Again, up to you, right? I mean, I can talk about anything you want. Again, all my lessons are on YouTube. I'm on Twitter, very active. Thank you for listening. See you next time. Bye.
Thank you so much. So, I thank you for joining also the Discord server, because so that the conversation can keep going. Sometimes with the Zoom chat, you just, close down Zoom and then you lose all the chat. So it's good if you want to address some other questions that are coming in on the Discord server. So, and the conversation can also continue offline.
I will follow up and type.
And we'll wait for your poll to decide on the topic for Friday.
Yes. Also, I can talk about control as well if you want to move things, right? Robots and things. So again, it depends on what is the largest interest. I will address, I will try to satisfy your interest, right?
Okay.
But please, the chat next time.
We will have the chat enabled on Zoom as well for Friday. That's for sure.
I'm so used to that, and I'm like, oh my god.
No, it's okay.
Well, I think, Alf, that still the interaction with the audience was very good.
Okay. Yeah, but it was.
You assimilated very quickly, and I think they had very good interaction.
It was not rehearsed, but anyway. So enjoy your lunch. I see you on Friday. Take care, right?
Thank you.
Thank you.
Bye-bye.